Hello and welcome back for day two of working with parametric equations. We're going to start looking at some examples on page 3 of your parametric packet if you want to use that to follow along. And the question of the day is, are monsters good at math? And I would say no, unless you count Dracula. Now let's look at some examples that are parametric. Eliminating the parameter is the heading that's at the top of this page. We were hinting at the fact the other day that parametric equations, or the graphs of parametric equations, also have an equivalent picture that could be expressed rectangularly in terms of x and y. So today I want to specifically go through converting back and forth between the two forms. It says sketching a curve represented by a pair of parametric equations can sometimes be simplified. So what we're going to do today is hopefully going to make graphing a little bit easier for us by finding, we'll say, a rectangular equation. And by rectangular, we mean just in terms of x and y, that has the same exact graph. Maybe if we can use our previous knowledge of graphing normal xy functions, it could go quicker and we wouldn't have to make a full out table like we did on the last page for every single parametric equation we graph. And there's a good set of suggestions in a little flowchart in this first example. Let's just say you have this random set of parametric equations you're interested in graphing quickly without having to look at a table. Well, Step 1 says, pick one of these two equations, whichever is more convenient, because it doesn't matter which one you choose, and solve it for t, get t by itself. I'm thinking they're both pretty easy to solve for t. Maybe the bottom one is a little bit nicer because just one move, right? Multiplying the 2 over gets t by itself. So in the bottom equation, you get t equals 2y. So we've got that solved for t. Step 2, we got to sub into the other equation. So the other equation said x equals, and instead of writing t squared minus 4, let's write what we just got, 2y squared minus 4. See how that looks. We could simplify. Now we have a rectangular equation, believe it or not, all in terms of x and y. We can make this x equals 4y squared minus 4. Is that looking like a conic section that you recognize? Perhaps a parabola, only y is squared and not x? And we want to graph this conveniently, so maybe we want to just put this equation into standard form, huh? So we will get the squared term on one side, so anything that has to do with y on one side, anything that has to do with x on the other side, equals 4y squared. And then 4p, if you remember, came over to the other side. So 1/4 x plus 4 equals y squared. This is the equation in rectangular form that has the same shape as these parametric equations, right? But it's in terms of x and y and something that we've been studying so far in this unit. Where's the vertex of this parabola? Great review. H and k, 0 or -4, comma 0. So we've got a vertex over here. It's going to open up, down, left, right. Well, we see y is squared, so we're going to pick some kind of sideways. And we see 4p is a positive value, right? 4p equals 1/4. And you get 16p equals 1, and p is 1/16. Like that. So we're going to travel in the positive direction to get to the focus if you wanted to put the focus on there. This is not going to be my best, but it is a skinny sideways parabola. If I plugged in 0 for the x variable, I would get 1 and -1 for the y's. So I do believe it's pretty easy to get the y-intercepts. And I'll actually give this one the arrows as if I'm graphing it rectangularly. But that wasn't too bad, and it didn't require a table to have to construct it. Now, I'm sure I could go back and use a little table to figure out my exact orientation of the original parametric function, but it was just kind of nice that some easy algebra got it in terms of something I'm familiar with. And that's what I want to try down here. So these guys look a little bit different. In 4, 5, and 6, you're presented with a set of parametric equations where there is a fraction involved in each one of them, and I notice a square root on the bottom of the fraction. Keep in mind that these original parametric equations aren't defined for all t. I mean, this one is, but I don't think this one's defined for all t, and that should come into play when we go to graph these. I want to see if we can follow the steps above with number 4. I want to try to eliminate the parameter as suggested here and get this as one equation that's rectangular in terms of x and y. So here goes. This is kind of fun. So pick an equation. I picked this one because I only saw one t in it, and I want to solve for t. And I might want to get rid of the square root right now. Risky move, but it'll help simplify. We'll square both sides. So x squared equals 1 squared over that square root squared. So you just get t plus 1. Start solving it out, right? I'll multiply both sides by the denominator. I want t by itself, so I'm just making algebraic moves, divide by x squared. And I'm going to leave this, instead of getting it as one fraction, I'll leave it as two separate parts. I think that looks good. 1 over x squared minus 1. So you have one of the equations now solved for t. Step 2, take this back up to the other part of the parametric equation, and let's sub in for both of those t's in terms of x. You get y equals 1 over x squared minus 1 over 1 over x squared minus 1, and then plus the original 1 that was sitting in the equation previously. So plus 1 on the bottom there. Now to simplify, right, so that we can see if this will look like an easy equation that we're comfortable with graphing, you've got some stuff canceling on the bottom. Up top, let me leave it sitting for now, 1 over x squared minus 1. But we can get rid of these ones on the bottom so that you just have the fraction, 1 over x squared. Complex fraction, we want to handle that. We want to bring up the denominator and flip it. So y is going to equal the numerator, 1 over x squared minus 1. I'll throw the whole thing in parentheses. Instead of divided by this fraction, times the reciprocal of that fraction, so times x squared. And we can write this simpler, and you're going to start to recognize what shape this should be. Bring the x squared into both parts. So the first part I think is a 1 minus x squared. And this is going to be our guide. This is going to make this set of equations easier to graph by hand. So I got to think about what I know about this curve. Well, I know that it's a parabola that's opening down, and I know it's shifted up a unit. I could actually sketch what I know about that curve now, but I'm a little bit nervous about domain of this versus domain of the original. And here's what I mean. Would you agree that this equation is defined for all real x? I mean, there's no real number that you're not allowed to plug in there, square, and subtract from 1. So that means that this new equation that we found ourselves is defined, or the domain of it, is all real numbers. So say for all real x. Well, that's fine, but we came up with this one ourselves, and we want to stay true to the original domain of the parametric equations. And I'm specifically looking at this one. This, I don't see many restrictions on t or y for that second part of the equation, but for the first one, I'm just going to draw an arrow this way. For the original parametric equation for the x component, you need to keep that denominator non-zero, and you can't take the square root of a negative and get a real number. So for that reason, in the original equation for x, I'll just put x in parentheses, not defined for all reals. We need the square root of t plus 1 to be greater than 0, not equal to 0. We can't divide by it. We need it to be greater than. Solving this inequality, the inside has to be greater than 0, and we're only graphing it. The original is only defined for t values greater than -1. What does that do to your equation in terms of y and x? Well, if we can guarantee that t is always going to be greater than this number, that ensures that x is always going to equal 1 over a positive value. X is always going to be greater than 0. So we're going to amend the domain of our converted answer and only graph it for x being greater than 0. Just the half of the parabola where the x's are positive. So just to reiterate, because the original has a restriction on t, which keeps this function always positive, we need to graph this picture so that x is always positive. So I could actually just use, the advantage of all that work we did was just to use a parabola that shifted up a unit. It would have had a vertex up at 0, 1. I'm going to make it an open dot vertex, so I'm not including x equals 0 on the graph. Everything above it will work. If I just thought of my parent graph, I'd be going down 1 over 1 and I think down 4 over 2. I'm just going to graph that one side of the parabola with no arrow going down at the bottom. It's a little bit different here. I got to decide on the orientation, either the object's traveling up toward that vertex or down away from it. And I think our easiest bet to figure out which way this thing is oriented, to the left or to the right, would be not to plot a lot of points, but could you just plot a few? It's a waste of time if we're going to make a full-out table here, because why else did we do all that other work if we're just going to plot points? But it would be good to choose just two convenient values of t that could be plugged into those two original parts of the parametric equation, just to see if my arrows should go to the left or to the right. And I'm looking specifically at this part, and I want to pick easy values. Easy values for t that are greater than -1. I think 0 is a nice, easy value for t. I also think that 3 is going to be a good, convenient value to work with without a calculator. So 0 plugged into this equation for t gives you 1 over 1. Gives you 1 comma 0 into this one gives you 0 over 1. 1 comma 0. So up here at this down here at this dot here at 1 comma 0, that's what's happening at time t equals 0. What's happening at t equals 3? Can you plug 3 into both those equations? So 1 over the square root of 3 plus 1 over the square root of 4 is just 1 over 2. And then the y is going to be 3 over 3 plus 1, so 3/4. So at 1/2, comma 3/4, this point here, that's happening a couple seconds later. That's happening at t equals 3. This thing is traveling as t increases, it's traveling up toward the vertex. So I want you to draw your arrows so that they're traveling to the left. And then this thing is finished. We didn't have to plot too many points. We knew what we knew about the graph, but the points did help us with the orientation. And I want to try this once or twice more. Can we look at 5 for a second? And let's just try the same thing. If you want to pause the video, try the first couple steps on your own. Solve this one for t, get t by itself, and plug that expression back into the other side to see if we can get a rectangular equation. And then unpause to see if I get the same thing as you. So let's solve it. I'll square both sides like I did with this one, 1 over t minus 1. I'll work to get t by itself. T minus 1 over equals 1. T minus 1 this time equals 1 over x squared. So I see some similarities between this and the last question. And t by itself this time is 1 over x squared plus 1. Now this needs to go into the other equation so that we can get a full rectangular representation for this set of parametric equations. So it's y equals twice, I'm going to plug this in for t. So 1 over x squared plus 1, and then plus the one that's originally in the function, since we plugged that in for t. On the bottom, 1 over x squared plus 1, and then look, you have a minus 1 that was in the original function, so those can cancel. You're going to get y equals 1 over x squared, I think plus 1, so plus 2, divided by 1 over x squared. And we can bring up the bottom and flip it now, so we can make this y equals, how about 1 over x squared plus 2? We'll leave the top, and then times the reciprocal of that denominator, so times x squared, very similar to what we did the last time. We can bring that into both parts, get y equals 1 plus 2x squared. I am comfortable with this type of function, right? It is another parabola we've got that shifted up a unit, and it's stretched a little vertically too, right? The y's are going to rise twice as fast. I have a feeling, judging by the original function, we need a domain restriction here too. The original is only defined, the x is only defined when t minus 1 is greater than 0. So t has to say greater than 1 in this case. As long as you're keeping t greater than 1, that's going to ensure this actual value for x will be 1 over a positive number. So we're keeping x positive again. X needs to stay greater than 0. Can you graph half of this parabola now? Shift up a unit, so we'll go up to 1, put an open dot there because we don't want to include x equals 0, and then you'd be traveling over 1 up 2 from there. You get a parabola that opens up, just resist the temptation to put an arrow on the end of that curve. We'll handle the arrows next. Make a little table. We got to pick the orientation here, and we're going to pick 2 easy values for t. So t, x, and y. I'm looking back to the original functions, and I'm aiming to make a perfect square on the bottom when I use a value greater than 1. Let's try 2 and 5 and see what you get for x and y. So I'll plug in here for x and y. You should get 1, 3 if you plug into the originals, and 1/2, 3/2. This should be enough information to at least just get us the arrows to finish off this picture. So 1, 3 is happening at t equals 2 seconds. This is t equals 2. What's happening at t equals 5, 3 seconds later? 1/2, 3/2, this is t equals 5. As time goes on, we are moving down this curve toward the vertex, and you have your orientation to finish off the picture. The last one says, I'll just start it with you. It says x equals 1 over square root of 3. I'm going to start it the same way. Feel free to pause if you need to too, if it feels like we're rushing. But we'll solve it for t. We'll make it x squared equals 1 over t when we square both sides. Tx squared is 1. And here t just equals 1 over x squared. Plug that into this one. So y equals 2 times 1 over x squared squared. And we get a rectangular equation, I think 2 over x to the 4th. This original is only defined for t greater than 0. And so that means x has to be positive again, right? X is going to be greater than 0 in this picture as well. That leaves most of the graphing up to you, and you can always check this with my answer key. But you know this graph. You know it's a hyperbola with asymptotes. It's got a VA at x equals 0 and an HA at y equals 0. And you can plot some easy points like 1, 2 on that curve. And really it's just going to be one of those two hyperbola branches. Plug in a couple easy t values to get the orientation. See you later.